Why, hello friends! Jen Foxbot here for another edition of Math Mondays. Da-na-na-na-na, yeah! Alright, welcome to the show where we look at math as a language. In this episode, we're going to continue our Algebra 2 exploration by talking about a concept called composition of functions. So that sounds like a scary term, perhaps, if math is not your favorite subject, but it's really useful. And it's really not super complicated when we understand what we're doing. So this will hopefully be a shorter video than some of the bigger topics that I did, like distance and midpoint formula from last week. So let's look at two functions, g of x. So we have a function that we're calling g. It's a letter, it's a nice little letter. And it means that we have a function that depends on our variable x. And I'm going to use a simple example. So we'll say g of x is equal to 2x plus 1. So in this case, we can plug in numbers and ask how g, our function, changes based on different number of x. So for example, we could ask, what is g of 1? Well, we plug in 1 for x. We say 2 times 1 plus 1. That gives us 2 plus 1, which is 3. So g of 1 equals 3. And we can ask, what is g of 2? And we just plug in 2 for x. 2 times 2 is 4, plus 1 is 5. And we can keep going. I'll do one more example. 2 times 3 plus 1. 2 times 3 is 6. And so we see 3, 5, 7. If you do more of these, you can start to see a pattern, and then you can use that to graph our function of g and see what it looks like. But what we are interested in today is talking about what happens when we combine functions. And so we need another function, and I'll call this function h, because I can do whatever I want within limits. So h of x, h is also a function of x, and let's say h of x equals negative 4x, oh I don't know, plus 2. And so now I want to ask the question, what is g of h of x? What does that mean? Well, that's okay. X is just a variable, so we can put in almost anything for x. We could put in g of pineapple. How do I draw a pineapple? This is a pear with some spiky ends. And so if I did that, then my function would look like that. Parapple. 2 times parapple plus 1. And we would be like, I don't know how to simplify that. And that's okay. That's where you leave it. Our g of parapple is equal to that, and that's fine. So that's totally acceptable in the right circumstances. And really, it just shows you that this x is a placeholder for whatever thing that we are putting into our function to see what happens to it. So sometimes you can think of a function as a machine where you put your thing in, you put your material in this case, typically with math, we're working with numbers, and out comes the outcome. And so a function is basically a mathematical machine that changes our input. And so we can actually plug in other functions into a function, and that's totally fine. It just takes a couple of extra steps to simplify it. So in this case, we plug in the entire function h of x for g, and that's going to look like this. So we have 2 times our variable, and this is where we put h of x in, because in this case, h of x is just our variable. And so we go 4x plus 2, the entire function of h, and then we come back to this plus 1 at the end of our g function. And now we can simplify. So 2 times negative 4 is going to be negative 8x. 2 times 2 is 4. So 8x plus 4 plus 1. And then we just simplify it a little bit. Negative 8x plus, whoops, I forgot my x. Negative 8x plus 5. So that is what g of h of x equals. Ta-da! That's all you got. And so in this case, we have something that's of a similar form. We have x to the first power plus a constant. So we still are dealing with the equation of a line. What happens if I ask what is h of g of x? Well, we just do the same thing. Except now we're plugging in g of x into this x within h. So we say -4 times 2x plus 1 plus 2, and we simplify in the exact same way. So we get -8x minus 4 plus 2 equals -8x minus 2. So what I want you to know here is that g of h of x does not equal h of g of x in general. If they happen to be the same function, then maybe they would be equal. But in general, it is not translatable. So unlike how you have 2 plus 3 equals 3 plus 2, I always forget, commutative? I think that's the commutative property, where you can flip things around and it equals the same thing. This is not true. But that makes sense, right? Because when we plug in, our functions are different types of machines. They do different things. And so we plug in an input into one machine, it's not going to necessarily give us the same output as another machine. Okay, so let's look at another example. Let's say instead of h of x, and I can erase that too, let's say that I have z of L. And I say that this is -4L plus 1. So in this case, I have a different variable, but that is okay. I can still ask, what is g of z of L? And I do the exact same thing. So I have 2 times -4L plus 1 equals -8, whoopsies, plus 1. Hopefully you caught that, viewer. So we have -8L plus 2 plus 1, -8L plus 3. Ta-da! That's it. So it's totally fine if our variable name changes. We don't have to stick with x if we don't want to. You can be creative and pick whatever letter you want. Or if you really want to do the pear apple or make up your own fruit, you can do that too. That's pretty much it. That is composition of functions. I want to end with a more complex example because I know in my experience in math class, the teacher would always do the most easy example and then give us the really hard problems on our homework, and I'd just be like, okay, here we go. So I'll do a somewhat more complicated example for you. And of course, I would love if you come up with your own examples and try them out. And let me know if you have any problems that you're running into and are like, how the heck does this work? So let's say we have a g of x equals 2x squared plus 3x plus 4. And we're going to do a q of x, because I like the letter q, of, oh, I don't know, 2x plus 1. That's an easy one to do. Okay, so now g of q of x equals, I plug in q of x into g. And the reason why I'm underlining this is so that you can see that this goes in for x. Okay, so now we have 2 times 2x plus 1, and that is squared, plus 3 times 2x plus 1 plus 4. So this is our x squared piece, so this goes into there, and this is our x piece, so that goes into there. And now we simplify. But we have to do order of operations. So in order of operations, exponents are one of the higher ones, or it's the highest one that we have right now. So we have 2x plus 1 times 2x plus 1 plus, and I'll simplify this one, plus 6x plus 3 plus 4. So this goes here to give us 6x, and then it goes here to give us 3. And then our 4 comes along for the ride. Cool. So now we have 2 times 2x plus 1 times 2x plus 1. So we need to do this first before we can multiply by 2. So 2x times 2x is going to give me a 4x squared. 2x times 1 is going to give me a plus 2x. 1 times 2x is going to give me another plus 2x. And 1 times 1 is just 1. And again, this comes down, plus 6x. 3 plus 4 is 7. All right, and now we can bring in the 2. But I want you to notice that this is going to give us 4x. So 2 times 4x squared is 8x squared. 4x times 2 is 8x. And 1 times 2 is 2. And then we have these pieces that we bring down, plus 6x plus 7. We're almost done! Okay. And the last piece is to combine the like terms. And so we have 8x squared. 8 plus 6 is going to be 14x. And 2 plus 7 is 9. Ta-da! So g of q of x is 8x squared plus 14x plus 9. So you'll notice that we still have the form of our g of q of x is still similar in that we have an x squared, we have an x, and we have a x to the 0, which is just 1. You can also say that it's a constant. Cool. All right, so there is a slightly more complex example, so I hope that gives you a better understanding of how composition of functions work. Basically, you just think about the function as a machine, and your input is changing, and depending on the input, the machine is going to do something different to your output. That's it. Please let me know if you have any questions about any of this or other math topics that you would like to tackle, and let's learn them together. All right, thanks for watching, and we'll see you next time. Bye!